don't understand it. Okay, anyways,
Selena Gomez.
so here, oh yeah, we already did the first part, right? Okay, we did part A. What were the answer? We just have to realize, okay, this is 40 ohms, this was 80 ohms, this is 1.5 volts, this is 3 volts. Yeah, we should see, yeah, I think we used whatever, some rules to figure this out. Like, I think we used loop rule or something. Yeah. Oh, yeah.
Oh, did you see Jeremy Lin's superior intellect?
All right. Thank you for the reminder. Part B. To what position should the contact be moved for ammeter A2 to read 0? Note, when this is the case, then if I is value blah, 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 then I was just... Okay, whatever. The question is, how do we get ammeter 2 to read 0? Okay, now, this is the 1 point... How did I draw that twice? Oh, I redid the thing. Okay. This is the 3 volts. So, what causes current? What causes current? Kevin.
Electric field.
Ah, okay, good. Some messages are getting through. That's excellent. Right? It's that gradient of electric fields caused by what? What thing do you put into the circuit to cause the gradient of electric fields? Randy. Let me make this way more simple. What things do you put into electronic stuff to make it work? Yeah, electricity. How do you put that in? Batteries. So batteries cause the electric fields, right, by the difference in charge on both ends. Does that make sense?
Yeah.
What happens if I take 2 batteries, both the same voltage, and I connect them positive to positive, negative to negative? What happens? Nothing. Why does nothing happen?
Why does it accident?
Because there will be no difference in the gradient of charges. Does that make sense to you?
Does it also go back to lights do not?
Oh, sure, lights repel. But I mean, if you put one battery that's much bigger connected to the other one, right? It's gonna like kind of overshadow it or whatever. And there's going to be a difference. But with 2 batteries that are identical, does it make sense to you? There's not going to be any flow of charge, right? Because the gradient is going to be the same. So all we have to do, look at this. How do I, because remember, A2 is ostensibly right there. Does that make sense? Look at this circuit. How can I get no current to flow out of the battery? Because this is going to be plus 3 volts as they come out here, right? So how do I get no current to flow out? Oh, sorry, 1.5. Thank you, Ann. Sorry, 1.5. That's 1.5 volts coming out of there. So why is it going to go like, if it was just a simple circuit like this, this is 1.5 volts, why does it go this way? Because this is negative 1.5 volts, yes? So it flows that way. What happens if I take something, put it here, and make this 1.5 volts? Right? If I make the delta V across this 1.5 volts, what am I going to do to the charges coming out of the battery? Yeah, I'm going to stop them. Do you see it? Right? There has to be a reason to come out of the battery. So right now, if I adjust the resistances and the currents and all that stuff so that the electric potential drops across everything are the same, so like the potential after this, like the potential across here is 1.5, then I should be able to cut the current down. Right? Because right now it's going from plus 1.5 down to this, down to 0. So if I make this look like a battery of 1.5, then I can stop that. Yeah, there's no reason for it to come out. All right, and it's not going to. So This basically, it's kind of like I have to say this has to be 1.5 volts, which will make this 1.5 volts, and then that should be 1.5 volts. Something along that order. Okay, so let's see how we can do that. Let me double check, make sure I'm answering the right question. Then why is
We're
it
looking at beat
Wait, my
A2,
A1.
right? Integer A2.
Yeah, what's that?
We're looking for A2, right? Under A2 to read 0.
Yeah, we're trying to make ammeter A2, so we're trying to make I2 0.
Okay. We're not worried about A1, right?
I'm thinking what we're trying to do is adjust this resistance so that 1.5 volts of it is lost through AB, and then 1.5 volts of it comes here. Because then if this is 1.5 volts, then that should not come out. Right? Because I can take this thing and I can redraw it kind of like this. Right? Like that. And if I make these charges have 1.5 volts, then that means when these charges come over with 1.5 volts, nothing's going to flow. Does that make sense? They have no reason to go anywhere. Because the drop across this is the same as the drop across that. Okay, this, I can see it. So for B, yeah, so the reading of A2 is 0 when the currents, these two currents are going to be the same, like they're going to bump into each other. So then our AB plus that equals 120, so I think it's just a proportion of that. Oh, look at that, that's funny. That's, okay. That's pretty much what I said earlier. So, let me see. So do you remember what I said here? I said this won't let any charge out when the electric potential across this resistor is equal to that. And then look at this 3 volt battery, right? So what do I have to do to this 3 volt battery? What do I have to do here to make this B to C be 1.5 volts? Just half, right? You see it? Because if I use half this resistance for A to B and half the resistance for B to C, and they're both connected to 3 volts, how many volts are going to be used up on each half? 1.5, right? Half or 1.5. And if the voltage from B to C is 1.5, you see the battery doesn't do anything. And that's what I was saying. Yeah, exactly. Does that make sense? So if we look at it again, just look at this right here. If the electric potential across the battery is the same, because remember the electric potential across the resistor has to be opposite, right? It has to be like nothing, so that like the battery can push charges from plus 1.5 through the resistor down to that. So it has to be like a minus 1.5. But if I make it plus 1.5, then the battery won't do anything. Right? It's like, I don't need to lift this up because it's already at the height it's supposed to be. You get it? Like if I'm a battery and I come in and this is on the floor, I'm a 1.5 battery, then I pick it up from here, now it has energy. But if the book's already here and I come in, there's nothing I need to do. So if I make sure that 1.5 volts is used up in this resistor, in the A to B resistor, then that means there is 1.5 volts left when they come here. And if it's the battery's 1.5 volts coming out, yeah, I don't need to energize anything. It's already done. Okay? So there you go. That's the answer for that one. Yeah. So I think when you draw it out in something like this, it makes a little more sense.
So 1.5 volts.
Yeah.
Is the answer.
Well, the answer technically is 60 ohms for each.
Because it's half a day.
Half and half, yep.
Like the boat was.
Exactly. That place is expensive. Oh my gosh.
买了个烧的，
Is just in case we don't remember, this was 40 ohms, this was 80 ohms. And so we saw from logic before how to get that. All right, questions? Oh, sure, part A. For part A, what we did is we said, okay, how do we come up with the currents? They wanted A2 and they wanted A1, yes? Okay, so I'm just going to use the simplest, easiest thing I can think of. There are 3 rules in this chapter that you use consistently. What are they?
Kirchhoff's loop rule, Kirchhoff's
Okay, you really like those. So Kirchhoff's loop rule, Kirchhoff junction rule. Even more important than that is
Ohm's law.
Ohm's law, right? That governs the relationship between voltage and current as a function of resistance. So what I do is I say, all right, using the loop rule, there is one loop right there. Does that make sense? Okay, so from that, I can say, all right, I know the current of I know A2 is going to be, I use Ohm's law, V equals I over R. So I of A2 is going to equal to V over R. And that's going to be 1.5 volts over 80 ohms. Does that make sense?
Is that 80 you said? Yeah.
And then now if I know that, then I can calculate the other current as well. So then I just do the loop rule again over here.
Can you just do a loop roll like something
Yeah, whatever, do whatever you want. Remember we did that yesterday. I don't want to redo everything, but yeah. We went the big loop, went this loop, went this loop, all of them work. Okay? And just, why not, in order to let you see the book solution, because we can. That's what they did. They said the loop rule. They used Ohm's law with the loop rule to get this current. Then they went around the outer loop and they said EMF1, which was like 3 volts, I think, or whatever, minus I1 RAB minus E2. So basically they skipped VC on that big loop. Does that make sense to everybody?
Oh, so you just do the outer.
Oh wait, stop looking at that.
So you never have a loop that includes every single question.
In this one you can. Okay, and then from that, you just solve that way.
How come for the capacitor, the small second why do you start going back and then because are you traveling the positive?
Okay, say that again. What?
The origin?
Uh-huh.
Why do you call back instead of return?
Coming out of the battery.
So
Yeah, you always come from the positive side of the battery. See? And then if you want to be sort of sneakier, just say, okay, that's 1.5 volts because it's in parallel with this, which means that's going to be, yeah, so then you can figure out. Okay, questions? Yeah. Look at the battery symbol real quick. This is the battery symbol. That's the battery symbol, right? Which one do you think is positive? Would you guess? Oh, okay. I guess that's a matter of perspective. Okay, then you just gotta remember it's the long side. Okay, long side, the giver of life, whatever, I don't know.
You live longer.
Yes, you live longer, so you have more time, whatever. That's okay. Any other questions on that problem? Good discussion.